On the morning of September 1st, 1859, English astronomer Richard Carrington was sketching sunspots through dark filters. Around 11 a.m., he saw a sudden flash of intense white light from the area of the sunspots. The whole event lasted 5 minutes, but what followed about 17 hours later was even more remarkable. The Earth's magnetic field trembled as a massive solar storm hit our planet. This wasn't just any storm. It was a geomagnetic storm so strong that telegraph systems across Europe and North America went haywire. Operators received shocks, and machines worked even when unplugged. RRS, usually seen in polar regions, dazzled skies as far south as Cuba and Hawaii, turning night into day. According to NOAA, gold miners in the Rocky Mountains woke up and made coffee, bacon, and eggs at 1 a.m., thinking the sun had risen on a cloudy morning. This event, now known as the Carrington event, was the most powerful geomagnetic storm in recorded history, hinting at the sun's hidden power and showing us how vulnerable our world is to its celestial moods. Fast forward to today, 15 solar cycles later, and we stand on the brink of another solar spectacle, the upcoming premature solar maximum and the reversal of the sun's magnetic field. As the sun approaches the phase of its peak activity in its 11-year cycle, it promises increased solar flares, sunspots, and coronal mass ejections. While we marvel at the potential for beautiful auroral displays, there's concern for our technologically dependent society, its impact on our health, and the warming of the oceans. The maximum also comes at a time around the Artemis mission, humanity's return to the moon after more than half a century. So, what will the upcoming solar maximum do to our planet in the coming months? What are the anomalies in this solar cycle that NASA is concerned about? Finally, and most importantly, will the upcoming phase of the sun's activity risk the life of the astronauts of the Artemis mission on the moon? Everything on Earth owes its existence to the sun. As our primary energy source, the sun might look the same every day from our vantage point, rising in the morning and setting at night, a cycle that has been constant throughout human history. Yet up close, the sun is a dynamic ball of plasma. It's covered in sunspots, flares, and other features like prominences and filaments that can outsize our planet. Essentially, the sun is a massive ball of hot gas that's always changing. But this change follows a pattern. On average, every 11 years, the sun undergoes a cycle of increased and decreased activity known as the solar cycle or Schwabe cycle. We are currently observing the 25th cycle of such activity, since systematic records began in 1755. But how did scientists notice the sun's activity changes over time? The key to this discovery lies in sunspots. Sunspots are temporary dark areas on the sun's surface, looking darker because they are cooler than the surrounding areas. The temperature in the center of a sunspot is between 3,000 and 4,500 Kelvin, much cooler compared to the surrounding area's temperature of about 5,800 Kelvin. They are caused by intense magnetic activity and sometimes can be as big as Earth. When astronomers started to keep track of these sunspots regularly, they noticed a fascinating pattern. The number of sunspots went up and down over a cycle of about 11 years. They also observed changes in the size of sunspots, the area they covered on the sun, and where they were located. A solar cycle starts with a few sunspots, known as the solar minimum. Then, as more sunspots appear, it reaches a peak called the solar maximum. After this peak, the number of sunspots begins to drop, marking the end of the cycle. Another interesting pattern is where the sunspots appear. At the beginning of a cycle, sunspots show up at mid-latitudes on the sun. As the cycle progresses, they move closer to the equator. This movement creates a pattern that looks like a butterfly when plotted on a graph called the butterfly diagram. This diagram is a great way to visualize the solar cycle's regular pattern. For a long time, astronomers kept a record of solar activity by observing the behavior of sunspots alone. But as technology improved, they noticed two more things that changed over a solar cycle. The first was the solar magnetic field. The sun is a giant magnet with a north and a south pole. The sun's magnetism lies at the heart of its dynamic features. Astronomers found that the magnetic field goes through a complete reversal of polarity with each solar cycle. This means that the solar magnetic north becomes south, and the south becomes north. The pole reversal occurs around a solar maximum, marking the end of the maximum and the transition of the cycle to its minimum, and importantly, marking the cycle's midpoint. This phenomenon remains one of the most intriguing and unsolved problems in solar physics, as we still don't understand why the magnetic field reverses polarity throughout the solar cycle. While the reason for polarity reversal remains a mystery, one feature of the sun may be playing a major role in this. The sun rotates in a non-uniform fashion, spinning at different speeds at different latitudes. At the poles, it rotates slower than at the equator. This is called differential rotation. It is believed that the sun's rapid differential rotation causes the plasma to drag magnetic field lines around, causing them to get tangled and twisted as they eventually reach the surface and create sunspots. Sunspots and other instabilities weaken the field lines even more, reducing them to zero and giving them a chance to rearrange and reappear at the poles with opposite polarity. Even though polarity reversal is a regular and predictable event, it remains one of the most intriguing unsolved problems in solar physics. Another aspect of the sun that changes with the solar cycle is its overall activity, including solar wind, solar flares, and coronal mass ejections. This activity reaches its highest point at the solar maximum and its lowest at the solar minimum. Because of these findings, monitoring solar cycles now involves looking at solar activity and polarity reversal, in addition to counting sunspots. But does every solar cycle have the same intensity and last the same amount of time? Not quite. There have been solar cycles as short as 9 years, and as long as 14 years since we began observing the sun closely. This means the 11-year period is an average of how long it usually takes for the sun to go through its cycle of activity. Each solar cycle is also unique in how intense it is. This is measured by the total number of sunspots. Yet there have been unusual periods in the history of solar observation that left scientists puzzled. One such period is the Maunder minimum, from 1645 to 1715, when very few sunspots were seen, about 50, compared to the usual 40,000 to 50,000. This time of low solar activity coincided with the Little Ice Age, when the North Atlantic region experienced colder than normal temperatures. Another period, the Dalton minimum, from 1790 to 1830, also saw fewer sunspots and was linked to lower global temperatures. This happened during solar cycles 4 through 7. Then there was the modern maximum, from 1933 to 2008, which had higher than usual solar activity starting around solar cycle 19. Now we're in solar cycle 25, and it's a shocker. Based on past cycles, scientists thought this one would be mild. But so far, the sun's activity is not what was expected, showing us once again how dynamic and unpredictable our star can be. Scientists first noticed the sun's activity changes over time by tracking sunspots, temporary dark areas on the sun's surface that appear darker because they are cooler than their surroundings. The temperature in the center of a sunspot ranges between 3,000 and 4,500 Kelvin, compared to the surrounding temperature of about 5,800 Kelvin. These sunspots are caused by intense magnetic activity and can sometimes grow as large as Earth. When astronomers began tracking sunspots regularly, they noticed a fascinating pattern. The number of sunspots rose and fell over a cycle of about 11 years. They also observed changes in the size of sunspots, the area they covered on the sun, and where they were located. A solar cycle starts with a few sunspots, known as the solar minimum. As more sunspots appear, the cycle reaches a peak, called the solar maximum, before the number of sunspots begins to decline, marking the end of the cycle. Another interesting pattern lies in where sunspots appear. At the beginning of a cycle, sunspots tend to show up at mid-latitudes on the sun. As the cycle progresses, they move closer to the equator. This movement creates a pattern resembling a butterfly when plotted on a graph, a visualization known as the butterfly diagram. This diagram is a great way to visualize the solar cycle's regular pattern. For a long time, astronomers tracked solar activity solely by observing sunspots. However, with advances in technology, 2 additional changes have been observed over solar cycles: the solar magnetic field and solar activity, including solar flares, wind, and coronal mass ejections. The sun's magnetism lies at the heart of its dynamic features. Astronomers discovered that the solar magnetic field undergoes a complete reversal of polarity during each solar cycle, with the solar magnetic north becoming south, and vice versa. This polarity reversal occurs around the solar maximum and marks the end of the maximum and the transition to the solar minimum, acting as the cycle's midpoint. While scientists still do not fully understand why the sun's magnetic field reverses polarity, differential rotation where the sun spins at different speeds at different latitudes may play a role. This rapid rotation can tangle magnetic field lines, resulting in sunspots and weakening the field further, allowing for polarity reversals. Solar activity, including solar wind, flares, and coronal mass ejections, also fluctuates with the solar cycle. Solar maximums are marked by increased solar activity, while solar minimums experience lower activity. Although the average duration of a solar cycle is about 11 years, some cycles have lasted as short as 9 years or as long as 14 years, with each solar cycle varying in intensity. For instance, the Maunder minimum, 1645 to 1715, saw very few sunspots, while the modern maximum, 1933 to 2008, experienced unusually high activity. The current solar cycle has surprised scientists with its intensity and premature peak. When this cycle began in December 2019, scientists predicted a peak around July 2025, with approximately 115 sunspots. However, recent predictions now expect the peak between January and October 2024, with an estimated 137 to 173 sunspots, highlighting the dynamic and unpredictable nature of solar activity. Understanding the impact of this increased intensity and early peak requires examining X-class solar flares. Solar flares are powerful bursts of electromagnetic radiation triggered by the reconnection of twisted magnetic fields. Flares are classified into B, C, M, and X classes, with X being the most intense. The Carrington event was linked to an X-class flare. Since the start of this solar cycle, several X-class flares have erupted, including one that caused a blackout on Earth in December 2023. With the sun's activity intensifying, questions arise about its effects on Earth, such as its role in global warming. While solar activity can influence Earth's climate, the data shows that solar activity alone cannot account for the recent increase in global temperatures. High solar activity also poses potential risks for NASA's Artemis missions to the moon. Solar storms can damage electronic systems and disrupt communications, but they also provide some protection from harmful cosmic rays. Despite these challenges, increased solar activity brings one positive outcome: more frequent auroras, offering breathtaking displays of the northern lights in regions like Canada, Alaska, and Norway. As we prepare for the solar maximum, it serves as a reminder that we are part of a much larger cosmic system. Meanwhile, recent discoveries, such as the James Webb Space Telescope's discovery of the farthest black hole, continue to expand our understanding of the universe.